Fine. Hi, everyone. I'm Andreas. This is joint work with Chris and Bhavya. So let's start real quick. What is Dyck Reachability and why do we care about it? It's a simple graph problem. You're given an alphabet sigma of different parenthesis types, and you're using this alphabet to construct the language of all properly balanced parenthesis strings. This is also known as a Dyck language. And on the right, you have a graph, a directed graph. The edges receive labels from the alphabet. And the task is to answer reachability queries on this graph. Only that now we only care about paths whose edges along the way have labels that produce a string that belongs to the language. For example, here X goes to Z because we have this blue path whose label is a properly balanced string. But X doesn't go to W, even though we have an edge from X to W. Right? And this is used as the algorithmic basis for a wide range of static analysis. In this talk, I'm going to focus on the first two, alias and data dependence analysis. So fine, this is an important problem. What's the status of it? Well, Dyck languages are a class of context-free languages. And every algorithm that I know of for the problem essentially is very similar to the classical algorithms for CFL parsing. Right? So it has cubic complexity, and even though it was improved by a log factor about a decade ago in this conference, we have strong indications that this cubic bound holds strong. So we don't hope to get anything better, in particular, no polynomial improvements over this bound. On the other hand, this bound is often prohibitive in real-life applications, especially if you want a lightweight static analysis. Right? It turns out that depending on the application, we might encounter graphs that have specific structure, in which case we can hope for better algorithms. And I'm here today to give you two such cases. So let's start with data dependence analysis, in particular in the presence of libraries. So the task of this kind of analysis is to identify which variables may depend on which others. Right? So we essentially follow the fuse definitions in our program. Whenever you have an assignment, the left-hand side depends on the right-hand side. Right? So if you have a program like this, with some loss of precision, you represent it as a graph. You have one node for every line that defines a variable, like here, and we draw an edge from 1 to 2, because whatever we defined in line 2 depends on line 1. Right. Of course, if you want to increase the precision of your analysis, you carry it to the interprocedural setting. So for example, here we have three functions, h, f, and g, and h calls f, so that in order to deduce that p in line 3 here depends on y from line 2, you have to go through an interprocedural path. And in these settings, we use a parenthesis symbol for every different call site, and so in this way, we effectively filter out interprocedural invalid paths, like one that would start with a blue edge, would go down here, and then exit through the red edge. Right? This doesn't correspond to any real execution. So this is a Dyck reachability problem. Now, of course, the way we write software nowadays is that we don't write everything from scratch. Right? Our code depends on huge libraries which offer some advanced functionality. However, when we want to make some analysis on the client side, right, we have to also consider the library side in order for the results that we conclude to make sense. But since these libraries are huge and they are used multiple times, one appealing approach here is to try to perform the analysis on the library side once and create some kind of summaries. And when you plug in your client code, you use only this summary information to analyze your client, hopefully avoiding the cost of reanalyzing a huge library. Now, there are reasons why this doesn't always work. One of them is the presence of callbacks. So if you think that you are analyzing this function g here on the library side, and you have a callback call f here, then whatever results you're going to deduce very much depend on how the client implements it. Right? If f is implemented as f1 on the left, then you have that 3 depends on 2, right, through this path again, whereas if f is implemented as f2, there's no dependency between 2 and 3, simply because this red path here is interrupted. Right? So we have to give up on our hopes on forgetting entirely about the libraries. We have to use them somehow, and the challenge here is to try to make it so that the client analysis depends as little as possible on the library, right? So what's the status here? So there are a couple of approaches on this. So our setting is as follows. We have a large library of size n1. You can think that you have n1 number of nodes in your data dependence graph on the library side. And you have k1 call sites. So these are the different types of parentheses symbols. And on the client side, we have a data dependence graph of size n2 and k2 call sites. And the assumptions we make here is that n1 is much larger than n2. And on each side, the size of the graph is larger than the number of call sites. Right? So as I said, one approach is to do Dyck, or what I call here a CFL reachability on the library side. So you pay a cubic cost for this. However, the information that you compute might not be effective, so that when you plug in your client of size n2, you might have to analyze the whole graph again in the worst case. There was an interesting approach proposed 3 years ago, which is that of using tree adjoining languages, which is a class of mildly context-sensitive languages on the library side. And with this approach, you can take care of callbacks to some extent, not completely. So you're happy with paying a much higher cost on the library side, right? N to the 6 instead of n to the 3rd. But since now you're more effective in your summarization, you create some summaries of size s here. And you're hoping that this expression to raise to the power of 6 here is better than paying n1 to the 3rd, essentially. Right? So I'm here to tell you about a new approach we have, which significantly improves this bounds. In particular, we managed to pre-process libraries on linear time effectively linear in the size of the library. And when the client becomes available, the dependence on the library side comes at an almost logarithmic term. Right? So how did we manage to do this? Well, we found that the graphs that arise in these data dependence graphs have special properties, and we exploit these properties to bring the complexity down. So in order to give you an intuition about this, I'll try to briefly sketch how this Dyck reachability algorithm works. So in a macroscopic view, we have a big data dependence graph, which is an interprocedural graph. We have these label annotations here on the edges. But in reality, this graph consists of many smaller graphs. So we have one data dependence graph per function. And these local graphs don't have labeled edges inside them. We only use labels as we transition, as we make calls and returns. So we transition from one graph to the other. Right? And the problem that essentially, the way that the problem is solved here is as follows. We start by doing some regular reachability locally on each graph. Right? And at some point, we discover that an entry node reaches an exit node, like here, 7 reaches 8. And since we have this information now, we're going to add a summary edge to the caller graph down here on the call side from 4 to 5. And as we have added this edge, this creates some new reachability information locally in this graph. We find that 4 now reaches 6, 3 reaches 5, and eventually 3 reaches 6. This is another entry to exit pair, so we add a new summary edge further down, and so on. So one way to view this process is as if solving an incremental reachability problem locally in each graph, iteratively. Right? You find some new edge, you insert it, you need to infer new reachability information now locally in this graph. You use this new reachability information to add new edges, and so on. Right? So, and most of the time is actually spent in doing this kind of local reachability. So what we have observed is that each of these graphs here, even though the big graph can be complex, each of these graphs here are very simple graphs. In particular, they can be characterized as graphs of low tree width. Now, I don't have enough time to precisely describe tree width. I'll just quickly mention what it is. So the tree width of a graph is just an integer parameter. It's a positive integer, which in some sense, in some very precise sense, quantifies how similar the graph is to a tree. And in fact, we have that the graph is a tree if and only if its tree width is 1. And the intuition here is that since trees are typically easy to handle algorithmically, at least easier than arbitrary graphs, low tree width graphs are also somewhat easy to handle. Right? In particular, what we managed to obtain is we managed to construct a reachability oracle that operates on low tree width graphs and supports edge insertions and reachability queries, both in logarithmic time. Right? And what we do is we use these oracles as black boxes to perform Dyck reachability in the same principle that I described here. And this brings the complexities down. Right. So let me now switch to the second type of analysis that we tackled. This is May alias analysis. The task here is to find out whether two pointers may point to the same heap object at runtime. Right? And one way that this problem is formulated is as follows. Again, with some loss of precision, you go from your code to a graph representation where you have a node for every variable, and you have extra nodes representing your heap objects like O1 and O2 here. And every time you have assignments here, you draw edges from one node to another. Right? So in the end, we can deduce that W may point to O1 because, well, W is reachable from O1. And one other way of increasing the precision of our analysis is making it so-called field sensitive. Right? And what this means is that as we make assignments and we read from fields of composite objects like W.f here, we keep annotations put field and get field in our graph here, and we make sure that whenever we have a path that witnesses reachability, right, this path, whenever this path sees some get field label, this matches with a previous put field label that you encountered earlier in the path, and the two fields match, right? So for example, here, O2 flows into V because, well, O2 is assigned to Z. Z is put into the field F of W, and then we're again reading from field F of W into V. Right? So this is, again, a Dyck reachability formulation of the problem. It turns out that in several applications, we deal with special graphs here, which are bidirected graphs. The idea is the following. Your graph is bidirected if whenever you have an edge from X to Y, like here opening a parenthesis, you're guaranteed to have the inverse edge closing the same parenthesis. So this is an if and only if statement. Right? And these graphs arise very often in demand-driven alias analysis. So the question is, given this extra property now, can we do anything better? Indeed, we can. A paper came out about 5 years ago in PLDI, which nicely shows how you can lower the complexity of Dyck reachability from cubic down to quadratic. And in fact, the average case complexity goes down to n log n. Somehow you have a new algorithm for this problem. In fact, we can take the complexity down to n times alpha n, where alpha n is the inverse Ackermann, so this is practically linear. And for the average case time, we're truly linear. Okay. And moreover, this is optimal. This is the best you can hope for. So let me try to give you a quick intuition of why bidirected graphs are easier to handle than arbitrary graphs. The idea here is that reachability on bidirected graphs is an equivalence relation. Right? Every time you can go from X to Y, it means that you have a path, right? And at some point you see a closing parenthesis, you know that this cancels out with some earlier opening parenthesis. And bidirectedness here guarantees that you can traverse the same path in reverse. And along the way, you're going to see complementary edges. Right? So the closing parenthesis here opens down here, and the opening parenthesis up there closes down there, so that the two again cancel out. And the same path in reverse witnesses the reverse reachability, namely that Y also reaches X. So the whole challenge here is to try and compute strongly connected components on these graphs fast. Well, the underlying principle for doing this is the following. You can essentially perform the same operation iteratively. Every time you try to identify 3 components so that some node from X goes to some node of Y while closing a parenthesis, and you have some node of X going to some node of Z, also closing the same type of parenthesis. And here you can deduce that Y and Z form actually one big strongly connected component, so you have to merge them. To see this in a concrete example here, we start with a graph of 4 nodes. So initially, every node forms its own connected component. We identify 2 closing parenthesis edges out of X. This means that the component of U, just U in this case, reaches V, and this is indeed the case through this path. So we merge the 2 into one big component. We proceed with the next step. Again, we identify 2 edges. One is a self loop in the component. The other goes outside the component to Z. And again, the 2 closing parentheses match, so we can put Z into the component, and at this point, we're done. And so in the paper, we describe an algorithm that identifies and merges components fast, and in fact, faster than before. And we also prove that this is the best you can hope for. So both in terms of worst case and average case complexity, the algorithm is optimal. Fine, let me quickly go through some of the experiments that we made. So we have made a prototype implementation for both Alias and data dependence analysis. And here we have used the experimental setting of the most recent papers we found on the topic. And this is a PLDI13 paper on the left and a POPL'18 paper on the right. And we compare against the methods that are proposed there. So in the case of Alias analysis, here are the results. So we have different benchmarks here on the x-axis. The numbers up here show the time taken by the slowest method to perform field-sensitive Alias analysis. And this is the percentage of the slower of the 2 methods, of the faster of the 2 methods. So yeah, the new algorithm is always faster, and most of the time is significantly faster. So we're happy with this. Let's go to data dependence analysis. Here, remember, we have 2 sites to analyze, right? A library and a client. So, and we have 3 methods to compare. We compare the TAL approach, the CFL approach. The 2 were compared in the POPL'15 paper. This is our algorithm. So you see here that for pre-processing the library, TAL most of the time is the slowest one, whereas we are down here, always the fastest. And when it comes to the client side, well, unsurprisingly, the CFL reachability algorithm is the slowest because it's very poor in summarization. However, if we want to compare the other 2 methods, our algorithm is faster in all cases but one, this one, right? So we can perform the client analysis faster, and at the same time, we have spent much less time pre-processing the library. Right? One other important thing to measure here is space, since you're analyzing these huge libraries. And things are maybe even more interesting here. So in the space usage, the TAL approach is always performs the poorest. So you always spend a considerable amount of memory for computing all the reachability relations computed here. Whereas, again, our algorithm is also much better in terms of space. And in fact, there is one benchmark not shown here, which is the serial benchmark. It consists of a fairly large library of about 70,000 nodes. In this case, the TAL approach hits the memory bound of 12 gigabytes. The CFL approach goes through using about, 3 times less space, 4 gigabytes. Our algorithm goes through using 100 times less space. So that's all I had to tell you today. We have, in conclusion, we have these 2 new exciting algorithms for doing, for performing certain types of Alias and data dependence analysis. These algorithms are considerably faster and better than before. They come with certain optimality guarantees, and we hope that they will be relevant to your research or analysis purposes. Thank you.
Yeah, thank you very much. The bidirectedness is very much reminiscent of analyses that can be formulated with undirected edges, both directed and undirected edges. And can I think of them as basically contracting actually equivalence classes of the undirected edges? In some cases you get, like in the 90s, there were a lot of applications of basically union find in doing these things in linear time. So for example, the work by Bjarne Stensgaard in 1996 on Alias analysis. And can you compare it or contrast it to that?
Yeah, I'm not aware of that particular work. Indeed, we're contracting equivalence classes, and one of the algorithmic ingredients that we use is a union find data structure. You need to also do a couple of other things smartly for that to work. But yeah, the underlying principle is, yeah.
Okay.
Union find classes.
Second question, you had some lower bound. You mentioned also that the work is transitive, what's sometimes called transitive closure hard, matrix multiplication hard.
Right.
Could you extend that by recent results by using the strong exponential time hypothesis, which gives actually absolute lower bounds, if that means anything to you?
Well, that's actually interesting. In fact, there is another result in the paper which shows that we also saw that the all pairs Dyck reachability in the general case is matrix multiplication hard.
Yeah.
So yeah. There was a hardness theorem already present showing 2 NPDA hardness. This is a different hardness result, different assumptions. But yeah, we have strong indications from various sources that we cannot hope to do better.
Is that similar to Lee's result, showing that for context-free languages in general?
I'm not sure.
Okay, right.
Hi, thank you for the interesting talk. I have a very minor question. So would you please elaborate your definition of SCC? Because our graph is bidirected, so in the original definition of SCC, every nodes are in the same strongly connected components. So I just want to know if there are some special definition in your SCCs.
Well, yeah. So these are not SCCs in the classical sense,
yeah.
But you can still
so
think
it's
of
the SCC with the information of the equivalence property, right?
Yeah. It's based on the
okay.
equivalence property.
Now I see.
Yeah,
Thank you.